100 million years ago, Southern California looked much different than it does today. So we have a lot of nice mountains in Southern California today. We had mountains 100 million years ago, but a lot of those mountains were volcanoes. We had massive amounts of molten rock, which we call magma when it's underneath the Earth's surface, rising up through the Earth's crust, reaching the surface and erupting as lava to build volcanoes. So when magma reaches the surface, again, we call it lava, and it can form nice lava rocks like what you see here. So this particular one is called basalt. I don't actually know if it is from Southern California. There are some places where you can find basalt in Southern California, but you can see these nice things like we've got some gas bubbles here and so forth. Now, magma that remains trapped underneath the surface can cool to form very different looking rocks. And depending on its chemical composition, it might make a major rock type that we find in Southern California today called granite. So here's an example of granite. I'm going to try and get this nice and close to the camera here. And all granites share some characteristics, and there are some important differences though, and you can see these differences in their color and their texture. We can see a couple of types of granites in Southern California, and I'll walk you through what those are and where you might find them. So one thing you might not know about volcanoes is that however much lava you see erupting on the surface, much more of that molten rock remains trapped underneath the surface as magma, and depending on its composition, it might form this granite. You can think of granite like this as the roots of the old volcanoes that used to exist here in Southern California. So this particular granite is one that I collected up near Idlewild in the San Jacinto Mountains, a bit east of Los Angeles. So what you're seeing here, each of these different patches of color are different mineral grades. So I'm going to go over what a couple of these are. So every granite that you find is going to have a lot of feldspar in it. So all of these white grains here are going to be feldspar. We also are seeing these dark black grains here. So these are a couple of different types of minerals which are very rich in iron and magnesium. That gives them their very dark color. So one in particular here, I'm moving it up and down in the light, and you can sort of see that very shiny surface there. That is called biotite. So that is a type of mica. So biotite, you can see it forming, if you see a nice large piece of biotite, it will form these nice shiny books of very thin sheets. And so you'll find a lot of biotite in magmas or in granite magmas. And some of these are going to be a little bit more dull, and they might be a little more elongated. This, for example, is an example of a mineral called hornblende. And you're going to have a lot of different variation in granites in the amount of those iron and magnesium rich, very dark minerals versus the lighter colored minerals, which here consist of feldspar. And also there are some quartz. So not the white or the black, but also this nice gray color. That is a grain of the mineral quartz. So you might be more familiar with quartz in its nice point form here. So this is an example called smoky quartz, but when it has a lot of room to grow, quartz will form these nice six-sided crystal spears. But when it is growing in magma, it is usually going to be one of the very last phases that actually crystallizes out of that magma when it's just about to cool solid. So it tends to take the shape of whatever void space is left around all of the other earlier crystallizing crystals. So there's a couple of different types of granites, as I had mentioned. And so here's another example of a granite. I collected this up near Big Bear in the San Bernardino Mountains. So one thing that you can see about this, it looks very different. It has a different proportion, very small crystals of those dark iron and magnesium rich minerals. And let me do something side by side. So these are examples that I cut with a rock saw, and to put the Idlewild and the Big Bear granites together, you can see that these are very different grain sizes. So sometimes when you have different grain sizes in granites, it means that the one with the larger grains cooled slower. One thing that you can also see here is that actually, it's a little bit more difficult to see here. So let me get you another example. So here is also an example that has much larger grain size. Now, this is also from up near Big Bear, but you can also see a color difference here. Now, as it turns out, these white and pink grains are both feldspar. Let me get that a little bit closer to the camera here. These are both the mineral feldspar. So why do we have this nice bright pink feldspar, whereas all the feldspars in this granite are white? Well, you can think of it analogously to when you leave something made of iron laying outside, and let's say it rains and you forget about it a few days, you come back and you find that it's covered in rust. And that rust has a very reddish color to it. And so what can happen to a lot of iron in some magmas is that it will chemically bond with oxygen and into a form where it has a more reddish color, and then that will be dissolved into feldspars and form this very nice pink color. So you can have some nice bright pink granites, and some granites where all the feldspars, you don't have that rusted iron, and so you're going to have all white feldspars. So more whitish gray granites and more pinkish gray granites. You can see both of these in Southern California. A lot of the granites, if you get up towards Big Bear, are going to have these nice bright pink feldspars in them. If you get up towards Idlewild, a lot of you're going to have mainly white feldspars. So that's one of those interesting chemical differences that you can actually see in granites and that you can see around Southern California. So there's a lot of this old 100 million-year-old or so granite in Southern California. That is the roots of these old volcanoes go east of Los Angeles, head down south in the mountains towards San Diego. So what happens when you have a nice big mountain that's a nice big chunk of rock? Well, as soon as a rock sees the surface of the earth, it's going to start to be broken down into smaller pieces. So it's subjected to wind, to rain. It's going to start being weathered, and those nice fresh outcrops of fresh granite are going to start to break down into smaller pebbles and to sand. That sand is going to get washed down the mountain, washed down into mountain streams, down into larger rivers, and eventually it will settle in a low-lying area like an ocean or a lake, and then it can form sandstone. There's also a lot of sandstone in Southern California. Here's an example. This particular sandstone, I'm going to try and get it close to the camera here, I collected up near Santa Barbara. The mountains north of Santa Barbara are mostly made up of sandstone. You can see these nice big yellow cliffs in sandstone. This is that's in a formation called the Coldwater Sandstone. If you're interested, this is an example of the Coldwater Sandstone. So one question you might have, if I told you that this thing is made of sand, and if you get a magnifying glass and look up on this really close, you're going to see individual sand grains in there. Why is it not just falling apart in my hand? Because if I were to just pick up a handful of sand, it would run through my fingers. So sandstones have been cemented together because once they are buried, there is always groundwater moving through them, and all groundwater has at least some dissolved minerals in it. So those dissolved minerals will precipitate into a sort of cement to glue together these sand grains and form a sandstone. So what you're seeing here, I'm going to try and get this close to the camera again. You're seeing there's a stripe of a different color here. So these are actually different minerals that are involved in the cement here. It's being cemented by different minerals here and here. So sometimes when you see stripes of different colors in sandstones, it's because of different minerals cementing the sandstone because of the groundwater that has moved through. So you can have quartz cement sandstone. You can have calcite, which is a calcium carbonate mineral. Sometimes you can have iron oxides, that very red rusted iron. If you see a bright red sandstone, then that is an example of a sandstone that's largely cemented by that iron oxide. So a lot of the sandstones in Southern California up near Santa Barbara, and if you head down the coast towards San Diego, a lot of the sand that makes these up is actually the remnants of those old volcanoes from 100 million years ago and the granite that forms their roots. But some of the sand also comes from further east in the desert. So what was happening in the desert, say 50 million years ago or so? Well, there are a lot of mountains in the desert today, but there used to be much higher mountains, and the crust there was a lot thicker than it is today. And think about a rock that is at the bottom of the crust down beneath a belt of mountains. So we know from when scientists drill into the crust that the further down you go, the hotter the rocks get. So you can imagine a rock sitting down at the bottom of the crust is going to be really hot, especially if it's down at the bottom of the mountain chain. And also rock is very heavy. So the more rock something is buried by, the more pressure it's under, the more it's being squeezed. And even though rock is solid, under the right pressure and temperature conditions, get it hot enough, squeeze it enough, it can actually flow like putty. Or think about squeezing toothpaste out of a tube. So you might imagine that something like that has happened here. This is called a gneiss. So this is an example of a metamorphic rock. If you heat up a rock and squeeze it enough, you can form new minerals in there, and you can also change the texture quite a bit. So this particular gneiss probably started out its life as a granite. So you can see here in the granite, these all these different mineral grains are sort of, the way they're pointing is sort of randomly oriented. So you have some of these sort of tabular pointy dark grains here, but they're not all in layers together. So once you get the dark and light minerals in layers together, we start calling it a gneiss. And you can see this gneiss has been sort of folded up here, a couple of different folds here. And that's just because it's been squeezed so much after it got hot and got subjected to so much pressure. This particular rock is from the Whipple Mountains. That's in Eastern California, sort of near Lake Havasu. And this is an example of what you can get at the very bottom of the crust when you have a lot of heat and pressure going on. So of the three main categories of rock that geologists will classify rocks into, we have igneous rocks, which cool down from magma or lava. So we have our nice, very voluminous granites that we find in Southern California. There are sedimentary rocks, of which an example is sandstone. We have a lot in Southern California. And then when you take those either igneous or sedimentary rocks and you bury them, you heat them and squeeze them, you can get metamorphic rocks, and we also have those. So we have a very diverse and interesting geology here in Southern California, and this is a very nice place to live if you want to become a geologist or just hike around and find lots of different very interesting rocks.